logarithms have some pretty amazing properties. The three properties I'm going to show you today are, I guess, so important that they're referred to as the laws of logarithms. And the way they kind of come up frequently is sometimes in calculus, you'll do a problem and do it from beginning to end and think you get the right answer, and then you state the answer is this: 1/2 natural log 36 plus natural log 3 minus 2/3 natural log 27. Then when you flip to the solution in the back of the book says that natural log 2 is the answer. As weird and as different as these two numbers look, these are exactly the same value. Now, I'll show you later why it's so, but these laws of logarithms can take a lengthy logarithm calculation like this and allow you to condense it into something a little more simple. So let me introduce you to these laws of logarithms. The first one says if you have log base a, and again, I'm using log base a generically. This refers to any logarithm, natural logarithm included. So if you have a logarithm of a factored product, so u times v is a factored product of two things multiplied together, then you can split that up into one logarithm for each factor written as a sum. So a factored product in a logarithm can split apart or be expanded as a sum of one logarithm for each factor. Okay, so essentially count the number of factors you've got inside there, and you can have one logarithm for each of them. So if you have 4 factors multiplied together, you can split that apart into 4 logarithms being added together. Similar if you have a log of a quotient, a numerator and denominator that are factored. And now in this example, this law states just one factor in the numerator, just one factor in the denominator. But the way it works is you can write this as a difference of 2 logarithms. Notice the factor from your numerator is a positive logarithm, log base a of u, and then you subtract the logarithm from the factors in the denominator whenever you split it up. Okay? And then a third law says that if you have a logarithm of a factor raised to a power, so a power on the factor in the logarithm, this third law says you can take this power outside to the front of the logarithm and make it a coefficient. So, a quick example of each of these. This first one, if you have, let's say, natural log of 5 times x times y. Okay. Now there's technically 3 factors inside there, so I guess a most general version of this says you can expand this to one logarithm for each factor written as a sum. So you have a natural logarithm for 5 plus a natural logarithm for x plus a natural logarithm for the y. And that's how you can use this first law to expand a factored product inside of a logarithm. Now my example's got monomials, but it applies to any kind of factors, monomials, binomials, however it's in factored form. This one, if you have something like log base 4 of, let's say it's 16 divided by, well, let's do this. Let's say 16a divided by m times n. Okay, so there's technically 4 factors inside here. Well, what this says is you can split up the quotient as log base 4 of 16a minus a log base 4 for the m and n. But then notice this property kicks in because you've got a factored product in this logarithm as well as the one in this one. So if you split this one up, this becomes log base 8 or log base 4 of 16 plus log base 4 of a, and then you're subtracting, I'm actually going to run out of room on this, you're subtracting, open parentheses, log base 4 of m plus log base 4 of n. Because, again, that's a factored product. It's got a minus in front of it. So when you use the first property to split this up into a sum, that negative actually distributes through. So when all is said and done, you can turn this into a log base, well, actually, log base 4 of 16 you would turn into the number 2, because that's what log base 4 of 16 is. So it would start off as 2 plus log base 4 of a minus log base 4 of m, and then again minus log base 4 of n. So sorry about the running out of room there. But notice what this tells you can do is if you count the number of factors in the original quotient, there are 1, 2, 3, 4 factors. Any numerator factors will split apart into positive logarithms, whereas denominator factors will become subtracted logarithms when you use the property properly all the way. So that's a handy way of kind of generalizing this second law of logarithms. The third one states if you have something like log base 7 of, let's say it's 5x plus 2 to the fourth. So that's an example of this. You have a factor inside, 5x plus 2 raised to the fourth, and it's inside the logarithms argument. This third law says you can take that fourth power out to the front as a coefficient and write this as 4 times log base 7 of 5x plus 2. Okay, and that's the correct use of the third law. Now notice, none of these laws say anything about expanding the logarithm of a sum or the logarithm of a difference. So don't make the mistake here of creating a property that doesn't exist. You cannot turn this into log base 7 of 5x plus log base 7 of 2. You're kind of making a distributive property for logarithms, which doesn't actually hold true. So be really careful about creating a property of logarithms that is false. So whenever you're doing the homework in this section, the first few problems ask you to take a single logarithm and expand it into as far as you can using these laws so that there are no factored products, quotients, or powers left on factors. So if I start with this first one, now if it's written this way in the textbook, one thing you're going to want to do is as you're writing it in your notebook to start the homework, any square roots or cube roots, anything that's written in a root form, you're going to want to rewrite it in an exponential form. So write this as log base 4 of 16 a to the third times b to the 1/2, because we'll see why when we get to expanding it, exactly why you need to do that. But yeah, radicals always need to be written as fractional exponents before you do your expansions. So now I've got a factored product inside here, a factor of 16, a factor of a cubed, and a factor of b to the 1/2. So there are 3 factors inside here. And so what the general version of this first law says is if you've got a factored product, you create one logarithm for each factor and add them up as you expand it. So this becomes log base 4 of 16 plus log base 4 of a to the third plus log base 4 of b to the 1/2. Okay, so that's taking care of the first law. There are no more products inside. I've taken the factors and written one logarithm for each, but then you want to use all the properties so that no exponents or powers on your factors remain. So I can use the third property here to bring the cube and the 1/2 power to the front as coefficients. But again, those will only apply to those 2 logarithms after you've expanded it. Now notice again here, there's a log base 4 of 16. If there's a logarithm that you can evaluate without using the calculator, go ahead and evaluate it. See, log base 4 of 16, that becomes the exponent 2. And then the third law of logarithms kicks in here. Bring that 3 to the front, and that becomes 3 log base 4 of a. And then plus 1/2 log base 4 of b. And you know you're finished when there are no more factored products inside any log arguments. That's a single factor of a, that's a single factor of b. There were no quotients to begin with, so we've got the factored products and quotients taken care of, and there are no powers left on the factors inside. So this is as far as I can expand that particular logarithm in example A. Okay. Now example B, let me separate these. Remember, you're going to want to use like a general version of this second law if you see quotients. What the generalized version says is you count the number of factors you've got inside, and you'll create one logarithm for each factor. So I've got an x, I've got a y squared, I've got a 5, and I've got a z to the third. There are 4 factors inside this quotient. So I know I'm going to need a natural log for the x, I'm going to need a natural log for the y squared, I'm going to need a natural log for the 5, and I'm going to need a natural log for the z to the third. Now, I'm just stating what the first 2 laws tell you. How many factors you've got in the logarithm, that tells you how many logarithms you'll split it apart into. Now, the signage that goes in front, this is an equal sign, not to be confused with a minus sign. The signage that goes in front of each logarithm depends on where the factor came from. If it was a numerator factor, the logarithms will be positive. So that means the logarithms that I split up for the numerator, that'll be a positive ln x, so no need to put a deliberate plus in there. But I do need to put a deliberate plus right here. And then, if you have any denominator factors, taking into consideration that this distributive property for the minus would apply to any factors that split from the numerator, all you need to remember is that denominator factors, when you split them up, become subtracted logarithms every single time. So you'll always get your signage correct if you let the position of the factor in the fraction tell you the sign of the logarithm when you split it apart. So that takes care of using rules 1 and 2 in one step. If you just count the factors and let the position of the fraction tell you whether they're positive or negative. Then I've got two uses of the third law right here. I can pull those exponents to the front, and then this will be completely expanded as natural log x plus 2 natural log y minus natural log 5, and then minus 3 natural log of z. So inside each of these logarithms, there are no more factored products or quotients, and there are no more powers left on the factors. So that's as far as I can expand that one logarithm. Okay? Now, just like Yoda taught us in Star Wars, you need to be able to unlearn what you've learned. So the next examples I want to show you are starting with expanded logarithms and then trying to condense them back to a form like this in our next video.